Okay, so today, if you remember anything about systems of equations, the way that we generally address systems of equations is that first you do solving systems of equations, Josh, right, by substitution and then by elimination. And that's basic, probably the treatment if you saw it at all. Here, instead, this first one, it doesn't say it, but this is all about solving systems by substitution, only the substitution method. And now it's not just limiting ourselves to linear systems. There could be nonlinear. There could be a quadratic in there or something like that. But generally, all they ever do is go quadratic and linear, and that's it. So it's mostly about substitution today. No, by systems of equations, what we mean is more than one equation with more than one variable. Usually it's two equations, two variables. Three equations, three variables. Four equations, four variables. If there's n equations, you must have n variables. You wouldn't be able to solve it if you didn't have as many equations as variables. I think in modeling the atmosphere for forecasting the weather, we have temperature, pressure, wind takes up 3 because you've got, on a flat surface, you've got the east-west component, the north-south component, and then the vertical component, that's 5. You have a humidity, that's 6. And then they have another one for evaporation condensation, that's 7. So how many equations do you need? 7. And there's 7. It's called the primitive equations. And that's what we stuff into a computer. That's what we were doing off at Air Force Base. Good. Tyree? Okay. Okay. Let me know. I mean, these are just examples of the kind of, you're reading a problem, and in the context of the problem, they ask you to find two things. And when you see that in your mind, you're supposed to say, I need two equations, right? These come from actually chapter 6, which was the chapter before the one we're doing now. And even then, they thought, you know enough about systems to have thought about that, right? Here they had two cranes lifting a weight that was suspended in the middle of them, and you had find a tension in each crane. Okay, right there, there's two things you don't know. You need two equations, right? This comes from chapter 11, which now instead of, this is essentially on a flat surface, this is in 3 dimensions. You've got cables holding up a weight which is in the middle. Find the tension in each of the 3 cables. How many equations do I need? I need 3, right? However many things I don't know, that's how many equations that I need. And I know in calculus, for example, there are times when you get a problem. They don't tell you that's a system's problem, but you're supposed to understand, okay, there's 2 things you don't know, you're going to use 2 equations. So systems come up. Right? These are the methods that we have for solving systems. And we are probably going to focus on 3 of them, right? Which is substitution is what we'll do today, right? And then elimination is next class. After that, we'll go ahead and introduce matrices. Do you ever had matrices before? Right? I mean, it used to be something that we did in Algebra 2, but we don't do that anymore. So we'll introduce the matrices, and then we'll go back to, you'll see what this Gaussian elimination is, but we won't solve anything with Gaussian elimination. Does that word or name look familiar? Gaussian, where did we just see that? Say again? It was a model, right? It was an exponential model, Gauss. So Gauss is a very prolific mathematician in history. He did a lot of stuff, right? A lot of stuff. Okay, so we're going to do that, that, and that. But you'll definitely see this one. This one, if you look in the examples in the book, in this section that we're doing right now, they do talk about solving by graphing. But I don't want to get into, that aspect of it. I just want to solve, let's say, analytically, algebraically. So solving by substitution. And specifically right now, I'm talking about a 2 by 2, meaning 2 equations, 2 variables. Right? These are the procedures. Right? You solve one equation for one variable. It doesn't matter which, it'll matter which, sometimes in terms of, you'll see which one is probably the obvious choice. But you could pick the equation and pick the variable. Then we substitute for that variable in the other equation, solve, and then we substitute that answer into the result from the first step and simplify, which we're going to do this on the next slide. So if you want to copy these down and have them to the side, then we'll see. Done. Okay. So for example, right, here's a system of equations, 2 variables, following the steps, what's the first thing I should do? Solve one equation for one variable. Okay, it doesn't matter which one, which equation looks like the obvious choice here. Probably the top one, right? If you solve for x or y in this one, there would be a little more calculating to do, right? So in this one, for the first step, we're going to solve that, and we have y equals x. Okay, what's the second step say? Okay, so in the place of y, put an x, right? That's the second step. Now we have 5x minus 3 times x equals 6. Right? At that point, you have an equation to solve. That's the third step. So solve what you've got in front of you. That is 2x equals 6. So x equals 3. Right? But we need to solve the last step said, go back to step 1, plug this back in to the result from step 1, and then find the other variable. This is like an overly simplistic example, right? But in the end, that when I plug in that value of x, y equals 3. Right? So solve one equation for one variable, substitute for that variable in the other equation, solve what you get from that, and then plug that result into the result of the first step, solve for that. And there's your solution, x, y, 3, 3. Okay, here's a more word problem kind of thing. And let me read. This is from 7.1. Okay. I think these interest rates might be different. Yeah.
So you solve for y or it doesn't matter?
Doesn't matter. You get to pick.
No,
right?
I mean.
Solve one equation for one variable. You pick the equation, pick the variable. You get to do that. Right? So in this one, it says a total of 12,000 is invested in two funds paying 9% and 11% simple interest. What do they mean by simple interest? I mean, not compounded. Okay, they don't worry about the compounding part, right? Just simple interest, just you use those interest rates. Okay. And it also says, oh, I don't know if this is going to come in. Recall that the formula for simple interest is I equals PRT. I don't even know if that is here. Okay. The yearly interest, right, is $1,180. How much is invested in at each rate? Right, so they're saying we're investing a certain amount of money. Actually, we're investing a total of $12,000 in two funds. One of them pays 9%, one pays 11%. Right? The amount of interest that we're collecting from this investment is $1,180. Right? So we set up a system of equations. We know that if X is the amount invested in one fund and Y is the amount invested in the other, that X plus Y equals 12,000. Right? That's the total that we've got to invest. Right? The interest is how much are you getting back from your investment? Well, for the X, which is the amount invested at 9%, you get 0.09 times that amount, right? 9% of it. And for the Y, from the Y fund, right, you're getting 0.11 times that. We know that that amount, if you add it up, is 1,180 every year. So there's your two equations, right? That two equations, two variables, solve. So at that, now that we've got it set up, follow the steps. Solve one equation for one variable. Which one do you think you'd solve for? Probably the first one, okay? Does it matter which variable that we solve for here? It's going to be identical, right? So how about we solve for Y? That's our instinct anyways, isn't it? Right, so this one we could say Y equals 12,000 minus X. Right, there's our step one. Step two would tell us to substitute into this equation for Y. So this is 0.09X plus, let me take that off, undo. 0.11 times 12,000 minus X, and that equals 1180. Don't do this to me. Okay, solve. Right now we have one equation and one variable, solve. Right, 0.09x plus 12,000 times 0.11. $13.20. Combine like terms, right? These two. It gives us a negative 0.02x plus 1320 equals 1180. Subtract 1320 from both sides. Negative 140. Right. So x equals 7,000. Okay. So we step one, step two, step three, step four would say plug in your answer into the result of step one, right? Because right there you've already solved the y. It's the perfect place to substitute this for, right? Put that value up here, and you're going to get y equals 12,000 minus 7,000. So y equals 5,000. Right. So a little bit of setup and then follow the steps. Now these are linear. The last two that we did were linear, right? Because the x and the y's were all raised to the first power. Okay, the thing that comes next is nonlinear. Right, so one of our equations is actually quadratic. It's got x squared in it. But we still follow the same steps. Right? Solve one of those equations for one of the variables and substitute into the other equation. Which variable do you think we ought to substitute for? Say again? You know, for example, I would not want to solve the second equation for x, right? Because it's squared here, it's to the first power there. That would be way too complicated. I wouldn't want to do that. I really wouldn't even want to solve that one for x. Then I'd have to divide by -2 as the last step and then plug it into two different places, one of which it's squared. Probably you want to solve the first one for y. That sounds like the easiest thing. I mean, you could do this one for y. In the end, it won't be much different. But I definitely think I'd be solving for y in one of these. Like, I think I'm going to solve the first one for y, right? And we'll get y equals 2x plus 5. There's our step 1. Step 2, right? Plug that in here. So x squared minus 2x plus 5 plus 3x equals 1. X squared minus 2x minus 5 plus 3x equals 1. Combine like terms on the same side. Right? We've got x squared plus x minus 5 equals 1. Subtract 1 from both sides. X squared plus x minus 6 equals 0. Right, so it's a quadratic in standard form, equals 0. It's factorable. Right, this will give us, that will give us x plus 3 times x minus 2 equals 0. Right, so x equals 3 and x equals, negative 3 and x equals 2. Okay, but now you need to find the y values to go with that. So again, what was that step? Plug those into the result from step 1, right? This is the result from step 1, right? This was the result from step 1. So you're going to have to do it twice. For the negative 3, y equals 2 times negative 3 plus 5, which is negative 1. For the positive 2, y equals 2 times 2 plus 5, which is 9. You know, so since x and y's, 2 dimensions, we could say this is negative 3, negative 1. This one is 2, 9. I mean, this first one is a straight line. The second one is a parabola, right? So it's, the line is crossing the parabola in 2 spots. Mandy, you got a question?
Why didn't you plug into the greatest
To plug these answers? Because we're going, when we solved the first equation, right, for one of the variables, that was the result. That's where you want to plug into, right? I say, you know, the result of step 1 is the right place to put it. I mean, that's important because when we do the elimination, we get to a similar step there, and it's not really, you don't have an obvious choice for it, right? Where am I going to plug in to find the other variable? with substitution, you really do, because that first step, you made the perfect place to plug in that result, that whatever you got for x, just plug it in there and solve. Right? Here's another one, just to show, right? Solving a nonlinear system. Which equation do you want to solve? The first one for y is probably the right choice, right? So this will be y equals 2x plus 3. Right. Y equals 2x plus 3. No. You know, when I add y to this side, I add negative 3. I add 3 to get that over here. It's possible. Okay, now we've got to plug in for y here. June. Right, so that's 2x squared plus 4x minus 2x plus 3 squared equals 0. 2x squared plus 4x minus 4x squared plus 3 times 6x plus 12x plus 9. 2x squared plus 4x minus 4x squared minus 12x minus 9 equals 0. So now we need to combine like terms. We have 2x squared minus 4x squared, negative 2x squared. We have 4x minus 12x minus 8x. And we have a negative 9. Okay, it's a quadratic. I'm gonna change this by multiplying both sides by negative 1. This is going to be 2x squared plus 8x plus 9 equals 0. We all right with that? Correct me if I made a mistake there, because I might have. 2 times 3 times 2. I think that's right. Okay, now, what's that? Do what? Because I'd rather they're positive. If you'd prefer to use negative numbers on everything. I mean, I could see, you know, we're probably going towards the quadratic formula. Would you rather use all negative numbers in the quadratic formula or all positive? I mean, and the fact that, you know, you had negative, 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 and a 0 on the side, you know, it's a pretty painless thing to do. Just multiply everything by negative 1. Deal with positive numbers, right? Okay, so now, if this was factorable, it'd be 2 times 9 is 18. The factors of 18 that add up to 8 don't exist. So it'd be a quadratic formula, right? So we would have to go x equals negative 8 plus or minus the square root of 8 squared minus 4 times 2 times 9, right? Divided by 2 times 2. X equals negative 8 plus or minus the square root of 64 minus I was hoping that we were going to get something. 4 times 2 is 8, times 9 is 72. So it's negative 8. So what does that tell you? You know, if you're talking about where are these things going to intersect in the plane, they're not, because they're imaginary solutions. So for our purposes, you get to that point, no solution. Okay. So here's a couple more kind of word problem-y things. right? A shoe company invests $300,000 in equipment to produce a new line of athletic footwear, right? Each pair of shoes costs $5 to produce. In fact, I changed that to 12. Okay, and sells for $60. How many pairs of shoes must the company sell to break even? Right, this is kind of a particular kind of word problem they do with this stuff. They're calling it break even, where you're trying to balance the cost with the revenue, right? When your cost equals your revenue, that's the break even point. I mean, at the beginning, if you invest $300,000 and you haven't sold a shoe yet, you're in the hole, right? You're losing money until you get to a certain point. So that point where you start to make money, that's the break even point. So they want us to come up with equations for the cost and equations for the revenue, and then they're going to ask, when do we break even? Well, let's see. The cost had an initial investment of $300,000, and it cost $12 for each pair of shoes, right? So that'll change. This part of it will change for every shoe that you produce. The revenue, you charge $60 per shoe, so you're going to pair of shoes, so you're going to get $60 times X coming back. Right? We want to know what's the break-even point. What are we going to do with these? Set them equal. Right? When is the cost equal to the revenue? So just make it 300,000 plus 12x equals 60x. And that's a pretty basic equation to solve, right? 300,000 equals 48x. So x equals 300,000 divided by 48. 6,250. Does anything seem wrong about that problem? I mean, what I'm wondering is, if this X here represents what? Every pair of shoes that they've made, right? What does that represent? Every one that they sold. You don't necessarily, you could make a lot of shoes and not have sold every one. Those are not necessarily representing the same thing. That presumes that every one you make is sold like right away. And it's probably not the way it works. I mean, don't you think for a certain kind of shoe, there's probably inventories. Every store that sells them has got a whole back room full of them. But it would be nice if it worked like that. Okay, and then the last example, almost the same thing. Movies. The weekly ticket sales for a new animated movie decreased each week. At the same time, the weekly ticket sales for a new horror movie increased each week. Models that approximate the weekly ticket sales are here, right? So the sales equals 108 minus 9.4x, where the x represents the number of weeks each movie was in the theater. And this one is for the horror movie. Okay, we want to know, after how many weeks will the ticket sales for the two movies be equal? What are we supposed to do with these two things? Set them equal to each other. Right, so this will be 108 minus 9.4x equals 16 plus 9x. Okay, let's add 9.4x subtract 16 92 divided by 18.4. 5 weeks. So, I mean, what it says is that the movie that was going down was actually really popular the first week. And then this is the one that was not very popular in the first week, but kept growing. Okay. So, in a sense, these are systems of equations. In the end, it's like that whole first step of deciding what to do. You're just setting one equal to the other. Let's see. Did we do all this stuff? We used the substitution method for linear, for nonlinear. We did not do the graphical approach. And we did some word problems.